always find such a solution. Okay? It's not necessarily analytic, meaning I might not be able to find an analytical solution for this equation, but you can see that the interface profile always has the same structure. Why is this? You can read it from this equation. You see here, this is the gradient of m squared. Okay? And here's the difference between the values of the potential. If you revert this in some sense, you have a double well potential. And as I have drawn, if I want to construct an interface solution, I have to go from here to there. So I have to get over this hill. So what can I infer from this relation? Well, you see, this is equal to this energy difference. So I can say the gradient of m that I find is proportional to this difference. Which means that from this shape I can immediately read off that the gradient will be steepest in the center of the interface. So no matter what's the detailed shape of that double well potential, the interface will always be of this type. With the steepest gradient in the middle and going smoothly out of the equilibrium thing. So it might not be exactly a hyperbolic tangent, but the interface solution will always somehow look like a hyperbolic tangent. Okay? So it doesn't really matter what kind of double well potential you use. And that's why everybody uses this polynomial, because it's the simplest and because there is an analytic solution. But it's important to understand that this is not limiting. If for some reason you want to use another double well potential, you can. It will not change the physics. Okay, another point where this is useful for is to calculate the surface free energy. Because we have here a domain wall between the two phases. You already might have heard many times that such a domain wall always costs energy. And now we are in the position to precisely state where this energy comes from. You can also read it off from this plot. You see, if you're sitting here in an equilibrium phase, well, you are at the free energy minimum. If you're sitting here, you are at the same free energy. But if you want to put in a domain wall, you have some region in space where you have to go through here, necessarily, because you have to connect the two phases. Okay? So you have this space region where your order parameter is not in one of the equilibrium values. So it has to sort of go over that hill. That is, we have some space points where the free energy is higher than in the equilibrium states. So that means this domain wall solution will have a higher energy than the homogeneous phase. Okay, and that's the origin of the surface free energy. Now let me give a precise definition of this surface free energy, which I will call gamma. So this is the free energy of an interface state minus the free energy of a homogeneous state divided by the surface area. Okay, I just wiped out the equal partition relation, but anyway, I can write it down again. So what does it mean if I have a system like this, a three-dimensional system, and I have an interface here? So here, say here's the plus phase and here's the minus phase. Of course, I have to calculate the free energy of this whole system. So I have a volume integral. And then I have to compare this to a system where there is no interface, so say everybody is in the plus state. So the free energy of these two systems will be different. And I can subtract, I can form the difference. So this will be the total energy cost of this surface. But then, in order to get an intrinsic quantity, I should divide this by the surface area, and this by the cross-section of the system. Okay? Now, if you think about how you go about this, the free energy is an integral over this Ginzburg-Landau free energy functional. So that's a volume integral. Okay? Now, in both cases, for the system with interface and for the system without interface, you have integration along x, y, and z. But all the functions are constant along the directions y and z, because I have put my surface normal to the x direction. So these integrations just fall out, because the surface area is just the length along y times the length along z. So this division will just, in some sense, take out of these integrals the y and z direction. So I can write this as gamma is equal to the integral of my free energy. I can write the gamma is the integral of my free energy density with the interface solution minus the free energy of the homogeneous state, and this, no, I do not have enough space, but here you have just a dx. So the surface tension is given by a one-dimensional integral. So if I write this out, and now you will see where this equipartition relation comes out useful. Gamma will be, so what is this? An integral over 1/2 k dxm squared. This is the gradient squared term. So this is non-zero in the interface solution, but it is 0 in the homogeneous solution. So here I do not need to subtract anything from this, because I have to subtract 0. For the potential term, it's different, because here I have f double well of m of x. That's the potential in my interface solution when I have to go over the hill. And I need to subtract from this the value at equilibrium. So this is Fw at plus or minus 1, which correspond to my equilibrium states. Okay? And I need to integrate all of this with respect to dx. So this is an exact relation for the surface tension. And now I can use my equipartition relation that I have wiped out, but I will write again, because from this equipartition relationship we have just gotten that 1/2 k dxm squared is equal to f double well of x of m of x minus f equilibrium, so which is precisely a double well of plus or minus 1. So the two contributions in this surface tension integral are the same, which means that I can simplify them. So there is two formulas that are perfectly equivalent, which allow you to calculate the surface tension. One is the one that you find in almost all books, because you will often find the expression that gamma is equal to the integral of k dxm squared dx. And we will need this formula in the following as well. So, okay. So this you get when you replace this one by the gradient term. So you see there's 2 times 1/2 k gradient, so you just complete the gradient term. And then there is a second one, which is the integral. And now if I replace the gradient term, I just get 2 f of m minus f of plus or minus 1. Yes? And actually this integral can be used to get a simplified expression for this surface tension, which often allows you to calculate it explicitly. And for this, I will again need this equipartition relationship, because from this expression, I can, by inverting this, I can get an expression for the gradient dxm. So this will be, I have to multiply 2 by k here, and then I have here the f of m minus f of plus or minus 1. And then I have to take the square root of this here. So this in some sense tells you the exact relation of the hand-waving argument that I have given you before. The magnitude of the gradient is linked to the distance, to the height of the on which you are on the potential well. If you are here, your velocity is highest, and in the analogy, the gradient is highest. Okay? Now, why this is useful? Because now I can transform this integral. Because the problem why this is difficult to calculate is here my integration is of over x. So what I would like to do, this is a function of m. I would like to switch integration variable from x to m. And this I can do using this formula, because if I'm sort of physicist, like not so rigorous, I can say that this is dm by dx. So I can write that dx is equal to dm divided by the whole square root. I'm not writing all the terms. Okay. Which means that I can replace the dx here. And I'll write the result upstairs here. You see that is quite practical, because I have 1 over square root, and I have the same thing here. So in total, I will get, so let me see, let me make sure that I write the good things. Okay. So gamma will be what? I first have to connect the prefactors. I have a 2 here, and then I have a square root of 2 by k. So what I will get is I will get a square root of k here. And then I will get an integral over square root of twice f of m minus f of plus or minus 1. And then I get a dm here. And so here I have to integrate from minus 1 to plus 1. And just to show you on a concrete example how it works, let's take the 4th order polynomial. So for our f double well, that was h minus m squared by 2 plus m4 by 4. What do we have? F of plus or minus 1 is equal to what? It's equal to minus 1/2 plus 1/4. So this gives you minus 1/4. So that means if I form f double well of m minus f of plus or minus 1, you see if I subtract minus 1/4, this gives you a plus 1/4 here. And you see that this is a perfect square. So this will give you 1/4 h 1 minus m squared squared. Okay. if I put in this formula, you see that this is very nice because the square root will just take off the square here. So what I would have to calculate in the end is I will have some prefactors. So I will get in the end, what I will get is something like square root of k by 2. And then I will get the integral of the square root, and then I have, I will collect all the prefactors. So I have also a square root of h from this expression when I put this in. So I have a square root of h that comes here with the rest. And then I have just to calculate the integral of 1 minus phi squared, phi minus m squared dm from minus 1 to 1. So I hope you still know how to do that. So this is equal to m minus m cubed by 3 taken between plus 1 and minus 1. So that gives you 4/3, a simple number. So in the end, what you get is that gamma is equal to 2 square root of 2 by 3 times square root of kh. Okay, so this was a lot of calculations. Let us pause a little bit and reflect on what we have done and on the generality of these results. So, I have already mentioned that for the interface profile, no matter what you do, you can switch from this fourth order polynomial to another double well potential. We will get the same interface structure. So what happens to the surface tension? There's actually a very simple way to see that the scaling behavior of the interfaces is always the same. And this is the following. If I go to this free energy functional, dxm squared, okay, and then I write here the potential under the form that we have always seen, h times some function f of m, which is dimensionless. Now, I have demonstrated that I can do this for the fourth order polynomial. Of course, I can do this for all potentials because what is the physical sense of that constant h? The physical sense of that constant h is the height of this barrier in the free energy potential, right? Because this gives you the scale of the implied energies. Okay. So now there is a very physicist way of going about these things, which is called a dimensional analysis. That is, you see here you have a functional, and in this functional you have just two constants, that are the constants k and h. So you can look at what are the physical dimensions of these constants and see what you can do with it. Now, we have already had that before. F is an energy. If the little f here is a dimensionless function, that means the constant h has dimension of energy per unit volume. So the dimension of h is energy per volume, because the integrand is a free energy density, right? We integrate over space, so the integrand has dimension of energy per unit volume. Here in the gradient square term, precisely, you have a gradient squared. So you take off two lengths, because gradient is like 1 over length. So the dimension of k is energy over length. Because with two additional divisions by length, you get again energy coupled. So you see that from this, indeed, you can form two dimensionless, two other combinations with a physical meaning. One is k by h square root. Because if you do that, you see that this is a length. And the other combination is you can multiply the two and take the square root. So the square root of kh. This has the dimension energy per surface. So you see that these two constants fix you a length scale and a surface energy scale in some sense. So you can immediately guess that these scales have to show up somewhere. And indeed, in our calculation, we have seen that the interface thickness, meaning the width of this interfacial zone, is proportional to that. And we have found that the surface energy is proportional to that. Okay? And from this dimensional analysis, you can obtain that if you change the double well function from the fourth order polynomial to some other function, well, maybe the prefactors will change. There will be no exact 2 square root of 2 by thirds. It might be 0.7892. You might be forced to calculate this numerically. But the general scaling behavior will always be like that. That is, these two coefficients or these two terms in the functional fix the interface free energy, and they fix the interface width. Okay? And now there is, I just want to give you two very physical interpretations, hand waving, that explain you why this is this way. It's precisely, we have said that a system, an equilibrium system, wants to minimize its free energy. Let's look at these two terms separately, what they would like to do. If the gradient term was not there, what the double well term would like to have? Well, it would like to have that all systems, the entire system is somewhere in the wells. So the profile that minimizes this term alone is a step function. Because you stay in this well on one side and then you jump on the other side. So a step function would put the whole system in the wells. Okay? Now the other term alone penalizes gradients. So this term would like to have a homogeneous system. So it would like to flatten out the profile as much as possible. So the result is this term wants to flatten out the profile. This term wants to push it to a step. So in some sense, these are two antagonist terms. This term wants to make the interface wider. This term wants to make the interface sharper. And as a result, you get this diffuse but localized interface, which has this physical scale as its length because it results from two opposing trends. There's also a very simple interpretation for this one. And for this one, it's better. So let's give this a name, the length. Let's call it epsilon, which is done in many literature works. And let's eliminate here the constant square root of kappa with the help of this. What you get is square root of kh. You can also write it as epsilon times h. Okay? You replace square root of kappa as epsilon times square root of h. You get that this is just, the surface tension is just proportional to the thickness times the constant h. Now what does this mean? It's also very intuitive. As I have said some time ago, if you want to go from one phase to the other, it costs some energy because you have to get over the hill. Now the scale of the energy that you have to invest to get over the hill is given by the constant h, because this is the height of the hill. And this hill will contribute in the interfacial region, and the interfacial region has a width of epsilon. So you contribute this energy penalty over a width epsilon, and that's why the surface tension has to be proportional to the product of the thickness times the barrier height. Okay? So all of this is very intuitive, and it explains you why this free energy functional naturally contains domain walls with a domain wall energy and a natural domain wall thickness, which is the main strong point of phase field lines. Okay. Now all this was equilibrium. Let's start to look at some non-equilibrium phenomena. Okay. So in the remaining minutes, I will analyze with you two cases where the equation of motion comes into play. One is the motion of a domain wall when I apply a magnetic field, and the second one is motion by curvature. So and here again, the mechanical analog comes in very handy, as you will see. So now we put a non-zero magnetic field. So now our double well function becomes slightly different. So I will take the Landau polynomial that we have always had. So we have 1 minus m squared squared. And then I put minus mh, which was the contribution of the magnetic field. So what does this do? If I put a magnetic field, say I put a positive magnetic field, so I favor the up phase. If I draw the free energy as a function of m now, well, this will make my double well potential non-symmetric. Right? Okay. So it will look like this. So this is the well close to m equal 1. This is the well close to m equal minus 1. And so now I will have here an energy difference, a delta F, which will be equal to, in fact, 2h. Why 2h? Because the difference between the two equilibrium values is 2. I go from minus 1 to plus 1. I add a slope h, so the difference is 2h. So if I go back to the mechanical analog, remember here I had my potential V as a function of x, which was the negative of the double well potential. So now it looks like this. And I still would like to find an interface solution. That is, I would like to find the trajectory of a particle that goes from here, goes through the well, and comes to rest here. Now, from the mechanical analog, it's immediately clear that I cannot obtain this with the previous equation, because if I start the particle from here, it will arrive here with a finite velocity, so it will go over and go nuts. So this solution is only possible if I add a friction term. So now what I have to write, I have m dT plus d dtx is equal to minus dv by dx. Okay? So this is inertia. I have added a friction force, which is proportional to the velocity, and this is driven by the force that derives from the potential. So this is a standard equation for particle with friction. And now the question is, of course, what's that friction constant B, the friction coefficient B? Well, okay, I can derive a condition for this friction coefficient B. How can I do that? Well, I multiply this whole equation by dx by dt. So I multiply by dtx. What do I get? I get m dtx dttx plus b, oops, this is a dt, sorry, dtx squared is equal to minus dtx dv by dx. So why this is useful? Well, if you stare at this long enough, you see that it's a total differential. That is, this is 1/2 of m dt of dt x squared. It's like this, because if you derive this, you have the outer derivative which gives you this, and the inner derivative which gives you this. Okay? This term I cannot do anything, so it's dtx squared. And this term also you can write as a total derivative, because this is equal to minus dt of v. Because again, this is the outer derivative, this is the inner derivative. So now I can integrate over time. What do I get? Well, here I get a total derivative. So I get 1/2 m dtx squared taken between plus infinity and minus infinity, plus the integral from minus infinity to plus infinity b dtx squared is equal to v of plus infinity minus v of minus infinity. So what you see is the first term is 0, because I want to start from the particle with 0 velocity on one maximum, and I want to arrive to the other maximum with 0 velocity. So this gives 0. This is something that I don't know. So this is b times minus infinity plus infinity dtx squared. And this here is the potential difference between so this is a delta V, which is the difference between the two potential zones. And you see that this is an equation which fixes B, because I know the difference. This is known. This is a function of my. So this is 2h. This I know, it's a constant. So I need to time integrate over the trajectory of the particle, the friction, and there is exactly one value for the constant b, which will satisfy this equation. Okay. Now let's look at what this means in our analogy with the interface. If I come back to my analogy with the phase field, this means that here I would have b times integral minus infinity to plus infinity, and here I have dxm squared. And here I have the difference, so this is equal to 2h. And here I have the difference between the two values. I have to be careful about the sign. I want to go from this unfavored phase to the favored phase, so this should be positive. I think so. Okay, now how can I interpret this? Let's look at the phase field equation. Now you see the phase field equation is what we have written, what I have written down. I have that this is minus gamma delta f by delta m. Now we have calculated what is delta f by delta m. So this is the Laplacian of m plus f prime double well. So this is nothing new. But in some sense you can guess what happens, because I have this interface profile. Now I will draw it this way, because I have said I put a positive magnetic, I put a positive magnetic field. This favors the positive phase. So what will happen is that this domain wall will move, because the positive phase will gain and the negative phase will lose. So what happens, the spin should turn around here at the interface, and therefore the positive domain grows and the negative domain shrinks. So I suppose this is what happens. So I suppose that this interface moves with a certain velocity v. And now I'm interested in a stationary solution, so meaning I have switched on my magnetic field, and I suppose that I leave it on and it has always the same strength. And I suppose that after some initial transient, maybe the domain wall will settle down in a constant velocity. So I'm looking for this, what is called traveling wave solution. That is a solution that moves with constant speed. And for a traveling wave solution, I know that there is a simple geometric relation. I know that the time derivative is related to the space derivative. This is equal to minus v times dxm. Simply because if the gradient is like this, and if I move forward, then that means that my point has to move upward. Okay? So this is a simple geometric relationship that you can derive if you want to translate a curve. Then the time derivative and space derivatives are related by this rule. Okay? Now, if I write the complete equation of this, so where do I have? Where do I have space here? So I will apply this. I will have a minus sign, and I will divide by minus gamma. So I will have v by v gamma dxm is equal to, and then I will apply the functional derivative. So I have a minus kappa minus k dxxm plus f prime double well of n. So I just put this on the other side. V of gamma dxm plus k dxxm is equal to f prime w well of n. And here again, you see the complete analogy to the mechanical system. This was inertia, this was friction, and this was the force. Right? So the analogy is really very nice, because now it allows us to just apply the formulas that we have obtained. And what is the formula that we have obtained? Well, inertia doesn't play a role because it conserves energy. So what we get, the friction constant V here is the ratio of V and gamma. So we get that V divided by gamma times integral over minus infinity plus infinity of dxm squared dx is equal to the energy difference that is equal to 2h. Okay, we already have obtained a very important relation. You see, the velocity is proportional to the magnetic field. Okay? Which is kind of intuitive, because if there is no magnetic field, there is no motion. And if you put a small magnetic field, this is like a small perturbation, so it's quite reasonable to see that the velocity to first order must be proportional to the magnetic field. Now the question is, what is the constant of proportionality? Now I just want to say that this, in principle, is a non-trivial equation. Why is that? Because here we need to integrate over the profile of the interface, okay? And this itself should be the solution of this equation, right? So in principle, to solve this equation exactly, to calculate the velocity, you first need to solve this equation and then put in this profile in this integral and calculate it. Okay? So this is a kind of daunting task because this is a difficult equation. I don't know how to solve it. But there is something you can do, and that's what everybody does, and you can sort of justify it mathematically. That is, if you go to the limit where the magnetic field is small in some sense, you can suppose that the profile of the interface should be very close to the equilibrium profile. That is, you suppose that the profile is just a hyperbolic tangent, and this translates. Okay? To be more precise, and one can give mathematically a more precise definition of all this, but I don't think that I will get into this because it would take quite a while. You apply a magnetic field. In principle, you can write that your profile is the equilibrium profile plus a perturbation that would be proportional to the magnetic field. Okay, so you have a perturbed profile. Now, you see, if you put into this into the integral here, okay, so you get the 0th order term, which is the equilibrium profile, and then you get perturbations that are in powers of h. And what you can say is, okay, I take only the dominant contribution, which is the lowest order, which corresponds to the equilibrium profile. So this is an approximation which is valid in the limit where the magnetic field is small. Okay, and if I do that, I can actually solve everything. So if m of x is equal to the equilibrium profile m of x, because if this is the case, I know that the integral of dxm squared, we have had this before. Remember, that was one of the formulas for our surface tension. So up to the gradient coefficient gamma, k, this is just the surface tension gamma. And then I can just write that V is equal to 2h times big gamma. I insert this. So then I have a gradient coefficient here, and I have surface tension. Okay, so this is a complete expression for the velocity as a function of the magnetic field. And the only a little bit non-intuitive thing is that surface tension appears here. Okay, Now, I don't have a hand-waving explanation for that, but it's not random, because actually what happens is that this friction integral contains the same gradient expression as the definition of the surface tension. So both of those are linked to the fact that there exists an interface profile, and that the same interface profile comes into play when you calculate the surface tension and when you calculate the friction. Okay? But I cannot explain in the deeper physical meaning of why it's exactly gamma that appears here. Okay? So there's a few other things that are evident. For example, the velocity is proportional to this constant big gamma. The constant big gamma is the relaxation constant of the phase field equation. Okay? So that means actually this gives us a way to obtain a value for this constant gamma. Okay? Because in principle, domain wall motion under an applied magnetic field is something you can measure. So in an experiment, you can obtain what's the velocity as a function of magnetic field. All the other coefficients you know, because the surface tension you can also measure. The gradient energy coefficient you can obtain when you know the interface thickness, which is also something that you can measure in principle. So you can measure everything except this constant gamma. But if you measure the relation between V and H, you can fix a physical value for that relaxation constant gamma. And the physical meaning is, indeed, gamma is a friction coefficient. And it's for that you can only obtain its value by non-equilibrium measurements. That is, if you measure motion, you cannot get this value from equilibrium. Okay, so this is the first non-equilibrium phenomena, the motion of a domain wall under applied magnetic field. Now to wrap it up for today, we will have a last point which will be actually relatively short. So let's see, what do I need to leave? Motion by curvature. Or, in other words, curved domain walls. So up to now, I've considered straight interfaces, flat interfaces. Now what happens if we consider curved interfaces? So the situation I want to consider is, for example, a plus domain here, spherical with a radius r, immersed in a minus domain. And I'm going to look at the limit where the domain size r is much larger than the interface thickness epsilon. Okay? So if you picture the diffuse interface, it's something like this. It's not a mathematical line, it's sort of smeared out. This length scale I have defined to be the interface thickness epsilon, and I want to look at the limit where the domain is big, that is, its diameter is much bigger than epsilon. So, what do we need to solve? Well, we need again to solve the dTm is equal to minus gamma delta f by delta m. Yes? Always the same equation. And now I'm going to draw a conclusion from this condition here. So if I have a time evolution here, that means that domain will grow or shrink. Okay? So the interface will move forward or backward. But if the radius of curvature is much larger than this epsilon, I can make the same hypothesis as here. That is, I can suppose that the interface profile is approximately the equilibrium profile and that it will translate with approximately constant velocity. So I can do the same thing as before. That is, I can approximate this by minus v, and now I have to switch to a sort of cylindrical coordinate system, r, phi, and z. Well, I forget about z, so the relevant derivative here is the radial derivative, drm. And then I have to evaluate the, I will do as before, I will divide by minus gamma in order to collect these constants. So this will become a plus. I will collect the constants. And then I have to evaluate the variational derivative here. So this will be as usual minus k, and this time I have a Laplacian m. And then here I have plus f prime double by of m. So what's new actually is that now instead of having just dxx here, I need to evaluate the Laplacian in radial coordinate. So as you all know, this has two terms. There is first the second radial derivative drm. And then we have the first derivative, that is, we have plus 1 by r drm in a circular domain. In general, here I should put d minus 1 by r. D is the space dimension. So if you're thinking about the circle in 2 dimensions, this is 1 by r. If you're thinking about the sphere in 3 dimensions, that would be 2 by r. Okay, so this is the Laplacian, and here I have the derivative of the double potential. So now what you see is we have this term is new, so we have to think about what we do with that. And now I will again use the fact that I'm in this situation, and I will make the following approximation. You see here we have a drm. That is a gradient of the magnetization. This will be important only in the region of the interface. Outside of the interface, it will be approximately 0. So the only place where I need to take into account this term is the interface region. And the interface is at the radial coordinate of big R. So to a good approximation in this term, I can replace 1 by r, by little r, with 1 by big R, which is a constant. Okay? If this is a constant, then here this term becomes just constant time of first radial derivative of m. That's the same type of term which I have here, because here I also have a first radial derivative of m. So I can regroup these two terms. So I have v divided by gamma, and attention here there is a minus sign. So I have a plus, and here I have k times d minus 1 over r, and here I have a drm, and now here I have a minus k drrm plus f prime double derivative of m. Okay, sorry, this all belongs together. And what you see is that this is just the same equation that I had before for the moving front, except that for the moving front I have just this part, and now for the curved front I have this part that comes again, but it's the same, it's at the same place, so I can apply the same formalism and the same formula even that I obtained in the last section here. So I don't need to do any further calculation. what I get is that V divided by gamma plus K E minus 1 by R, and then I have here the gamma K is equal to 2H. So this comes, again, this is the friction, okay? And in the friction there is now two terms, one that comes from the magnetic field, one that comes from the relaxation of the phase field, and one that comes from the curvature here, okay? And this is the dissipated energy, because this is the energy difference between the two phases. And now this is a quite interesting formula, because you can apply this to two interesting special cases. Now, the first thing is, if we are at zero magnetic field, so if H equal to 0, what do we get? Well, if H equal to 0, then the right-hand side is 0, and okay, now there's something strange here.
No, it's like E is negative.
Yes, E is negative, but I'm missing, oh yes, okay. So this is fine, but I get that V is equal to minus kappa, and then divided by R. This is important, and here I have the K V minus 1. The only thing is, what's strange is, or not what's strange, what's not immediately nice is that I do not have the surface tension in here. But we should remember that this constant K is proportional to the surface tension. Okay? So what we have, that is the velocity is proportional to some constants that I do not write, but the important things are that is minus gamma, big gamma, little gamma, and R. What does it mean? If you look at this domain here, this has a certain radius of curvature. If I put zero magnetic field, well, the velocity will be negative, which means that the domain will shrink. Okay? And it will shrink until it disappears. Now, why is this actually quite logical? It's if I have no magnetic field, the two phases have the same energy, but I have here a lot of surface, and the surface, as we have seen, has an additional energy cost. So if the domain shrinks, that reduces the length of the interface, and so reduces the surface energy, and will thus make the total free energy decrease. So the shrinking of these domains is nothing but a consequence of the fact that the system seeks to minimize its free energy. And this formula here is very important because it tells you if the surface tension is the only driving force for your system, that is, if you have no free energy difference between the bulk phases, then the interfaces will move with a velocity that is inversely proportional to the radius of curvature. So it's proportional, if you call 1 by R, the curvature is proportional to the curvature, and it's always directed towards the center of curvature. Okay? And this is called motion by curvature. Now you see here, if I put this to 0, this falls out.
No, I thought that K and K from inside. No, it doesn't. Then it will end up with.
Does it fall out?
No. The K comes from somewhere else.
The K here comes from the gradient energy. The gradient energy coefficient. From the Laplacian. I mean, it's the prefactor of the Laplacian. So this is called motion by curvature. And notably, this is what happens for grain boundary, because grain boundaries are precisely in this case. If you have a grain boundary that separates two grains of the same phase, that means that the free energy of the two sides of the interface is the same. And so if the grain boundary is curved, it will move. And it will move in such a way as to reduce the grain boundary surface. So this is the physical effect that is at the origin of grain coarsening. Okay? So here I have done it for you for magnetic domains, but this phenomenon is perfectly general. If you have two phases of the same energy, and if the interface can move freely, then it will move by curvature. It will satisfy this, this relation. And the important thing, the driving force here is the surface tension, the surface free energy times the curvature. Because the surface free energy tells you the energy cost of the interface, and the curvature tells you in some sense by how much you can reduce the surface when you move inward. Okay, so this is perfectly general. Now the second important relation that we can get out of this is under what conditions actually a spherical domain is at equilibrium. That is, if we have V equal to 0, that is, we are looking for an equilibrium state in some sense. If we set V to 0, we get a relation that is K times T minus 1 by R gamma by K is equal to H. Now, this time the K falls out here. And so we see that gamma times T minus 1 by R is equal to 2H. Now, why this relation is important, it will show up in plenty of other contexts. This, in some sense, is a variant of what is called the Gibbs-Thompson effect. This time, we have a free energy difference between the two phases. Okay? That means if the droplet wants to shrink, it could reduce its surface area, but it would need to replace the favorable phase with the unfavorable phase. So there is a balance between surface and bulk energies. If the droplet shrinks, it has to pay in bulk energy and it gains surface energy. If the droplet expands, it gains in bulk free energy, but it has to pay in surface energy. And for exactly this value of the curvature, the two are balance each other. So the cost in surface energy and bulk energy are exactly equal but opposite. And that's why a droplet of exactly this size can be stationary in a magnetic field. Okay? So this equation in some sense expresses that the phase field model naturally contains the balance between bulk free energy differences and surface free energy. Okay? And this will show up in various contexts tomorrow and the day after tomorrow. So these are really two very, very important features of the phase field model. First, if you apply a driving force, which here I applied under the form of a magnetic field, the interfaces will move, and they will move with a velocity that is proportional to the driving force. Okay? And this relation can serve to fix the kinetic parameters of the phase field model. And second, if you have a curved domain boundary, there will be a driving force exerted by the curvature, which will have a tendency for the system to reduce its surface area. And if there is no counterbalancing force, this will lead to motion by curvature. And if there is a counterbalancing force, this will lead to what is called local equilibrium, meaning that the bulk free energy difference is balanced by the curvature. Okay, so this is two very important elements that are already present in this simplest of all phase field equations, and that we will find again in the course of tomorrow and the day after tomorrow. And with this, I'm done for today, and I'll be happy to take questions.
Questions?
Basically, I have totally lost you.
When there are functionals involved,
Huh?
when there are functionals involved, only variational derivative makes sense or complete full derivative also? What does it mean?
Well, okay, you are probably alluding to the calculation of the total free energy change that I made. Yes. So, as I have tried to explain, if you have a functional, what makes sense is a variation. Variation, what does it mean? Is in a functional you put a test function and you can only vary that test function. That is called a variation. Okay? So it's not strictly speaking a derivative, because you are not deriving with respect to one variable, you are changing the whole field that you input. Okay? Now, the total derivative is still meaningful, because the total derivative is the sum of all the local variations if you put a variation. So, how can I explain you? Let me write again the two expressions that we had in the first part of the course. I have told you that the change in free energy I can calculate by an integral, and here I put this variational derivative as we have defined it. And then here I put the variation of delta m of x, and then I integrate over dx. Okay? The physical sense of this thing is, to come back to my drawing, here I have x and here I have m. I have some field configuration that is like this. I change it to a different field configuration like this, and you see that the function changes over this whole range. What this means is, for each space point, I take this variation, that's delta m of x. I can, the variational derivative tells me how much the f varies when I vary m at that space point. Then I have to sum up this over all the space points where I change the field. Okay? That's the physical sense of that formula. Now here, I can put anything I want. And so I can put a delta m, which is the delta m by dt times delta t. Suppose that I have an equation which gives me the time derivative of m. Then if in a time interval dt, the variation of my function will be this. So this is of the same type of what I have drawn. That is, in general, I have to suppose that m changes everywhere. So my total change in free energy is given by this formula. I have to put this delta m here. Okay? And in this sense, then I can divide through by the dt. In this sense, I can define a total derivative of the free energy. Okay? So the total energy, total derivative makes sense. And in some sense, this is just like the chain rule, but you have to be a little bit careful mathematically, because formally f is a function of infinitely many variables. Okay? I don't know whether I have answered your question.
More questions?
Instead of circular sieve, if you have a square.
Aha. Okay. You are addressing a very interesting point. You see, I have told you I will place myself in the approximation where the shape of the, where the radius of the domain is much larger than the interface.